Imaging, high-speed cameras running at thousands of frames per second, time-lapse and macro photography, special cameras unravel the mysteries of our daily lives. So, what invisible processes are at work when we're cooking? Statistics rate the kitchen as the top location for household accidents, after the kids' playroom. They range from minor nuisance to lethal incident. Worst of all are cooking oil fires. A cooking oil fire can reach temperatures of over 300 Celsius. Following your basic instincts could turn it into a death trap. What happens if you use water to put it out? It's better to demonstrate the result outside. When water hits the superheated oil, it instantly vaporizes. But steam occupies almost 2,000 times more space than water. It erupts from the pot and carries with it the burning fat particles. A high-speed camera at 12,000 frames a second shows the detail. Never try to extinguish burning oil with water. The trick is to smother the fire, starving the flames of oxygen. One of the most frequent kitchen accidents is milk boiling over. It's particularly annoying as the fat and the proteins of the milk burn into the hob surface. A comparison with water shows what happens. What's invisible to the naked eye can be seen using a sensitive thermal imaging camera. When the water approaches 100 Celsius, small bubbles rise and burst at the surface, releasing water vapor. Now the milk. 90% of milk is water, but it also contains fat and protein. These are the tiny fat particles magnified 100 times under a microscope. When the milk reaches around 60 Celsius, the fat and protein clump together at the surface to form a firm membrane, the skin. The tiny bubbles are trapped and become stuck under the skin. The steam backs up. When the pressure becomes too great, the milk erupts suddenly and overflows. To avoid this irritating accident, you need to heat milk gently and stir frequently. Scientists have found an easier solution, using a magnetic mixer used in chemistry labs. A magnetic rod rotates in a glass beaker. It's driven by a second magnet below the hot plate. The hot plate can be controlled precisely, and the heat is evenly distributed in the liquid by the rotating rod. An invisible danger in the kitchen is the microwave when it's used to heat up drinks, in this case, water. Microwaves cause water molecules to rotate and rub against each other. It's an energy-efficient way of producing heat. Bubbles in the water usually begin to form at around 100 Celsius, but with very smooth glass, it may happen later. If you then want to sweeten your drink, the boiling liquid erupts. A high-speed camera unravels the sequence of events. 1200 frames a second, and the sugar cube hits the microwaved water. It boils instantly, erupting like a geyser. A spoon in the glass can prevent the misfortune. Many microwave manufacturers even suggest liquid should always be heated with a spoon in the container. That metal has no place in the microwave is a widespread myth. In extreme cases, it could melt a wafer-thin metal coating such as the gold rim on china plates. With the spoon in the glass, the water begins to bubble and boil in the microwave. Now that sugar cube doesn't produce a red-hot eruption. A microscope shows why. Bubbles can only form at nucleation sites, such as cracks or edges, just like the metal surface of a spoon. The surface of this glass, on the other hand, is much smoother and has no nucleation sites for bubbles to form. Instead, they form on the surface of the sugar cube with all its nooks and crannies. When it's dropped into the boiling hot water, masses of small bubbles instantly form, forcing hot liquid out of the glass. It's not unique to sugar. Tea bags or stock cubes produce the same dramatic effect. A heat-resistant pan is essential to fry meat. Water vaporizing tells you when the pan is hot enough. The oil too must be heat tolerant, and oils with fewer free fatty acids are better suited to frying. Now for the steak. The meat undergoes a huge transformation in the simmering oil. Proteins and sugar molecules are natural components of meat, and they react together to build aromatic molecules. They create the signature roasted or fried taste. Hundreds of these aromatic components develop in the fried meat. Many chemical reactions occur simultaneously, so many that they haven't all been researched in detail. In 1912, the French chemist Louis-Camille Maillard stumbled across the processes responsible for aroma development in baked and fried food, whilst he was exploring the structure of proteins. A thermal camera shows what happens. Between the steak and the hot bottom of the pan, the Maillard reactions are underway. Luckily, the center of the meat doesn't get hot enough to trigger the reactions, otherwise the meat would become tough. The processes inside the meat tissue are revealed under the microscope. Before frying, the proteins form an even net. But above 50 Celsius, they begin to clump together. It makes the proteins more easily digestible, but it also makes the meat tough. Time to turn the steak. Now it's brown with a crust. The heat has killed any microorganisms on its surface. Before serving, wrap the meat and let it rest at between 50 and 80 Celsius for 10 to 20 minutes, depending on the thickness of the steak. This thermal image shows the heat spreading evenly inside the meat to cook it through. More time, as well as ultra-modern techniques, offer alternative methods. This meat is being vacuum-packed. Heated in a bain-marie at low temperatures of just 50 to 60 Celsius, the meat cooks in its own juices. The thermal image shows the heat spreading evenly through the container. An hour later and it's cooked. There's no aromatic crust, but that's easily fixed with a blowtorch. It triggers the same Maillard processes as frying. The advantage of this method, called sous vide, is that the meat is cooked evenly and the results are reliable. Boiling food. Here too, cooking as evenly as possible pays off, so the food should always be fully immersed in boiling water. A lid traps the heat and saves energy. Just like frying, boiling also changes food both chemically and physically. The starch in potato cells goes through a dramatic transformation. Here the starch is stained to identify it. In the boiled potato on the right, it's clearly expanded. Under the microscope, the starch particles in the raw potato are clearly defined. During boiling, they swell by a factor of 100. When the pressure of the expanding starch bursts its cell walls, the potato is cooked. This collapsible steamer cooks vegetables more gently. It better preserves their precious vitamins, minerals, and aroma. Steam provides more heat than boiling water, but also acts more smoothly. That's because a layer of cool protective water droplets forms on the vegetable surface. On the left, raw broccoli still has clearly defined cell walls. But on the right, they've broken down during the cooking process. It means the vegetables are cooked through. It's even faster in a pressure cooker. It creates an increased pressure, pushing up the water's boiling point to 120 Celsius. Food cooks more quickly. A modern steamer means you can steam different foods with varying cooking times simultaneously. The steam is hotter in the bottom compartment and cools down on its way up. Cooking makes food more easily digestible, unlocks nutrients, creates aroma, kills microorganisms, and turns it into tender and appetizing meals. All thanks to the scientists in the kitchen. Preparing food from scratch can be a real pleasure, but it does take a lot of effort and time. So when is it worth going to the effort of making it yourself? Bakeries offer a large selection of different kinds of bread. Yet the main ingredients are always the same: flour, leavening, water, and a little salt. Everything is kneaded thoroughly. It's now that those little helpers in the mixture begin to perform their work. The leavening agents contain microorganisms like yeast or lactic acid bacteria. They're only visible when magnified 20,000 times. Millions of them produce the gas carbon dioxide. It allows the dough to rise and become lighter. But how does that compare to a traditional sourdough? Water and flour are mixed. The flour naturally contains vinegar bacteria and lactic acid bacteria. So within 3 to 5 days, at a temperature of 25 to 30 degrees, the dough rises on its own. The process produces acids, which later give the bread its distinctive taste. But bread making success or failure is determined in the oven. A thermal imaging camera shows what happens. Bright yellow represents temperatures of around 250 Celsius. The oven should be hot but not too dry, otherwise the crust will harden too quickly and the bread won't bake properly on the inside. Incredibly, a sourdough bread made in Berlin tastes different from one baked in London or Washington, because the many thousands of different bacteria strains in the world produce different amounts of acid. If the lactic acid bacteria were dominant, the bread would be milder. And when more vinegar bacteria produce the fermentation process, the bread will taste sour. There are over 180 different kinds of ice cream on offer in ice cream parlours across the world. But it isn't easy to imitate the professionals, even if at first sight the production process doesn't seem that difficult. In theory, it's very easy. Sugar, eggs, cream and milk are beaten together. Then the mixture is left in the freezer compartment. Time-lapse video from a microscope reveals a fascinating but undesirable side effect. As the ice cream mixture begins to chill, ice crystals start forming. This results in the dessert becoming hard, not the creamy stuff of the ice cream parlour. It's why professionals use ice cream machines. They churn the mixture as it chills, which constantly breaks down the ice crystals. Air is added to the mix. So the ice cream at -30 Celsius may be cold, but it remains airy and creamy all at the same time. For a similar effect at home, stir the cold ice cream with a mixer. Exotic chutneys, traditional jams, delicacies in a jar. A delicious and a useful way of preserving perishables. The first step to making kumquat marmalade at home is to boil the fruit to break down the fibres and release the cell contents. Adding jam sugar helps the marmalade reach its setting point. It preserves the fruit and contains the gelling agent pectin. This plant-based sugar naturally occurs in fruit, but usually not enough of it. During cooking, sticky three-dimensional net structures are formed that thicken the liquid. The mystery of the gelling process is revealed under the microscope. The fruit residue is the greenish-yellow structures, and they're bound together by pectin. But perhaps the easiest delicacy to cook at home is popcorn. It's said that Native Americans enjoyed making it a long, long time ago. Corn, oil, sugar and heat produce these airy structures, but you need to use corn with a high water content. The process is almost impossible to follow with the naked eye. But a high-speed camera running at over 3,000 frames a second catches that moment when corn turns into popcorn. Every pop is a miniature explosion. Water vapor forms inside the heated corn until it bursts the skin. Starch is emitted and expands to reach 4 times its original volume. And this works just as well at home as it does in a popcorn machine. When cooking at home, it isn't always possible to compete with the professionals, but you can take advantage of the same scientific processes available to them. And you do know exactly what's inside your food. Selecting the right kitchen utensils is a science in itself. The available range is vast, but what does a cook really need? A sharp kitchen knife is essential. It should have a cutting edge ground into a convex profile, which is easy to resharpen later on. The microscope shows that the edge is far from smooth and bears marks left by the knife sharpener. Only a really sharp knife will cut meat properly. When a knife can cut through a tomato simply under its own weight, then it's properly sharp. Bread knives have a double function to break through the crusty rind and cut smooth slices. Serrated knives have proven their mettle. The raised points of the serrated edge increase the pressure on the crust by a factor of 10. In slow motion, you can see the bread being literally sawn apart. Then the tiny arches begin their work by distributing the force evenly, slicing the bread carefully. What about a meat tenderizer? A perfect pork escallop should be around 5 mm thick. This is where the flat surface of a meat tenderizer can help. The blows loosen the connective tissue known as collagen. The escallop becomes flatter, larger, and very tender. The rough side of the meat tenderizer is less suitable. Although it has the reputation of tenderizing even the toughest of meats, its rough structure destroys muscle fibers. Meat juice oozes out and the cooked escallop will turn out dry. The choice of pans is overwhelming. Only those who know exactly which pan is best suited for what can find their way around. A Teflon pan seen in section to show its structure. The coating is made from PTFE, a technology in use during the US atom bomb projects of the 1940s, long before it ever reached the kitchen. Under the microscope, the structure of the plastic is visible. It's particularly smooth and doesn't chemically react with other substances. That's what creates the non-stick effect. But Teflon is easily damaged and scratched. It's quite heat resistant for a synthetic material, but it can't cope with temperatures over 270 Celsius. So you should never leave an empty Teflon pan on a high heat for more than just a few minutes. Over 270 and the Teflon coating is damaged. The pan becomes useless. Under the microscope, to the left we see an intact Teflon layer, and to the right, an overheated one. The plastic melts and loses its structure. During melting, some Teflon components are released, including the toxic gas hydrogen fluoride. It's carcinogenic and can cause acute flu-like symptoms known as Teflon fever. Unproblematic alternatives are pans with a ceramic coating. Ceramics are more heat resistant than Teflon, coping with temperatures of up to 400 Celsius, much higher than used for normal cooking. And the ceramic coating is tougher and more resistant to scratches. Only under the microscope can we see minuscule damage. The fried egg test and the non-stick effect of the ceramic coating is just as good as that of Teflon. Pots and pans of cast iron and stainless steel have taken our kitchens by storm. The thermal image shows how differently they conduct heat from the hob. While the stainless steel pot on the left remains cool on the outside, the cast iron pot on the right heats up all round. It also retains its heat for longer, which is particularly useful for slowly stewing meat. The cooking process continues even after the hob has been turned off, and that saves energy. But not all kitchen inventions are essential. Do we really need an electric sausage cutter? Or a machine that peels, cores and slices apples? Well, that's a personal choice.